Okay, good morning, afternoon, or evening, everybody. Welcome to the Mapping Global Urbanization from Landsat Data and High Resolution Reference Data webinar. This is your host, Jennifer Brennan. While everybody's logging in, we have two optional polls at the bottom left and middle portion of your page, and I'd like to thank you in advance for your feedback on these polls. I've got 2 p.m. Eastern Standard Time, so we're going to go ahead and get started here. What I'd like to do first is just go over a few logistics items related to today's webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any issues or have any questions, what I'd like for you to do is enter those into the Q&A pod located on the lower right-hand side of your screen, and this works like a chat. Today's webinar is being recorded. The recording will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earthdata YouTube channel within a few days of completion. I will send an email to all registrants with links to these recordings. Regarding timing, today's webinar is going to be 1 hour long. We've allocated 45 minutes to the presentations and live demonstrations with an additional 15 minutes for the question and answer period. And then once our speakers have finished with their presentations, what we'll do then is we'll transition to an optional final set of polling questions, and then from there we'll move directly to the Q&A period. And then just one final note regarding the question and answer period. Depending upon the volume of questions that are received, we will extend the Q&A period an additional 15 minutes to 3:15 p.m. for those of you who may wish to stay on the line. During today's webinar, we will have 2 speakers. Our first speaker is Dr. Eric Brown de Colston, who is a research physical scientist within the Biospheric Sciences Laboratory at NASA Goddard Space Flight Center. He will spend just over the first half, and I'm going to pull up today's agenda for reference here, of today's webinar, providing an introduction to the NASA Socioeconomic Data and Application Center, or SEDAC, Global Man-made Impervious Surface, GMIS dataset, and its companion urban extent dataset called the Human Built-Up and Settlement dataset. From there, we will transition to our second speaker, Sri Vinay, who is a system engineer at SEDAC and also the Associate Director of Information Technology Division at the Center for International Earth Science Information Network, or CESIN, which is located at Columbia University. He will provide a live demonstration that will show participants how to find information about today's feature datasets on the SEDAC web pages, and then also show all of you how to explore, visualize, manipulate, and then download these data products. With that, it is my pleasure to introduce today's first speaker, Dr. Eric Brown de Colston. Eric?
Yes, hello. Can you hear me?
Yes, thank you.
Okay, great. Well, thank you for the introduction, Jennifer, and thanks for to everybody who's joining us. It looks like we have a truly global webinar, which is very exciting. And so we have myself and Sri have an international background as well, and so we look forward to talking to you a little bit about these 2 global urbanization data sets that we recently produced and that are at the SEDAC. Excuse me. So my name is Eric Brown de Colston. I'm a scientist at the Biospheric Sciences Lab at Goddard Space Flight Center in Maryland. And my co-eyes on this project were Chengquan Huang and Panxi Wang from University of Maryland Department of Geographical Sciences. And it was really a collaboration between NASA, University of Maryland, funded by the Land Cover Land Use Change Program. And here are all the authors as well. We worked for about 1.5 years, almost 2 years, with Sri's team at SEDAC to make the data available online. And we're really happy with the way it looks and the ease with which we can serve this global data set. So I'll go ahead with the, Jennifer, if you can play the International Space Station movie, please. And I don't know how this will work for those of you on phones or on slow connections, but so this is a video from the International Space Station going down North America all the way down to the tip of South America. So you see the city lights, you see the clouds, you see the lightning on top of the clouds. And the reason I show this, I mean, it's very cool to look at, obviously, and we are doing some new research on the International Space Station. We have eco-stress sensor that was launched a few months back, and the JEDI sensor that is launching in a couple of months. And the reason I show this is also to show that how we can see that humans are really part of this Earth system that we study at NASA. Can I replay it? Yes, let me try to see if I can do that. We'll replay it again. But the point I'm trying to make is that we're recognizing that humans are part of the Earth system. We study the atmosphere, the oceans, the land, and when we're looking at the Earth from space, we see the impacts of humans on the land. And so it's very interesting. And as a geographer by background, it's very nice to also see the connections between, you know, the socioeconomic impacts of humans and what we observe on the land. And so it's very gratifying to have the data sets that we produced with Chang and Panchi being at the Socioeconomic DAC. And I hope you will all use them and give us some feedback. So let's go ahead and get back to the slides. I'm going to give you, excuse me, a little bit of a background on why NASA studies cities. And there was a question, you know, before this webinar, did you know that NASA studies cities? And so hopefully after the webinar, you'll be able to say, yes, I do. And so here we go. But yeah, just to give the perspective, as a principal investigator on a NASA project, we're really looking, and this goes across, so if you, I guess I'll move forward the next slides. But so we're studying land cover and land use change, whether it's deforestation in the Amazon, deserts, agriculture, urbanization. And so the work that we do is driven by just basic, research questions. And so some of the more generalized ones in terms of land cover and land use are, you know, how are global ecosystems changing? How are the forests, deserts, agriculture changing throughout the world? And the reason we're doing this is land cover maps are very important to drive the core scale climate models and weather models that we have. So it's very important to have an idea of land cover. The second one is what are the changes that are occurring and what are their causes? So here we recognize again that humans are the principal driver of change across the planet. And as well, you know, human decisions impact how land cover and land use evolve in different parts of the world. So urbanization in China, deforestation in the Amazon is driven by political, economic decisions that are, you know, human-based. So the third one is this aspect of prediction. So we are using the maps and the data that we have today to help us predict what the future might look like, you know, 150 years from now. So we have big computer models to help us do that prediction. And the last part is a little more of the science, is the so what, you know. So I live in Washington, D.C. and in the Chesapeake Bay watershed. So what happens to the water quality of the Chesapeake Bay if we replace everything by parking lots or different cover types? So in other words, what are the consequences of the change that we measure from space? So these are kind of the driving questions. So just to give you a little bit of background, since about 2007, the United Nations estimates that more people live in cities than rural areas, and we're seeing much higher growth in the next 30 years in Asia and Africa. And so that has, obviously, it's a rapidly urbanizing planet, and obviously important to study since we all live in cities, or most of us do, at least. But if you look at cities globally, there's still a relatively small footprint spatially. It's about 3% of the land or less, and so small footprint globally, but have a lot of impact, both regionally and also continentally and increasingly globally. So it's also interesting that cities, again, as a geographer, cities can be agents by themselves of land cover land use change. Like I did a study in New York City where, New York City restricts any kind of development in areas in the forests where their water supply is, but then, a lot of the waste from New York City gets distributed to landfills throughout the region. So it's very interesting to study that. And as well now with the sort of interconnection and teleconnections across the world, that places very far away can have an impact on land cover land use change in different parts of the world. So very interesting interconnected issues to study. So in terms of our objectives, the two main driving reasons is we had global data sets from Landsat, which became free in mid-2000s. And also we had a free archive from the National Geo-Spatial Intelligence Agency, which is high-resolution commercial data. And it provided opportunities to really map urbanization at a fine scale, and also looking at with future sensors. So really our principal objective was to use methods that had been developed for coarser scale satellites in the past, but to use the Landsat Global Land Survey data and then methods that were developed previously, and as well as part of the USGS National Land Cover Data Set. So I think I'm going to skip. If you're interested in these slides, I'd be happy to provide some, provide the slides on request. But really, urbanization has a lot of impacts, including changing the local meteorology, not only because of the heat islands, but also because of the vertical structure of buildings. And in the lower left panel, you see also the impact on stream flow. It tends to decrease the time between a rainfall event to when the peak discharges into rivers, but also increases that amount. So there's, the upper right panel is a picture of Houston after Hurricane Harvey, and a lot of the problems they had with flooding were related to the amount of impervious cover or surfaces that don't allow water to penetrate. So so please load up the Las Vegas time lapse, Jennifer. Thank you. And so you'll see here a Landsat movie available from the Science Visualization Studio at Goddard. And it's a time series from 1972 to 2015 of Las Vegas over time. And so on top of, I know there's many students out there dialing in, and so a lot of the work that we do in remote sensing is to look at these cool images and see how things are changing across the Earth. So what you see in Las Vegas, you not only see the growth in built-up areas, but you also see, if you kind of look, the water level of the lake next to it goes up and down as well with the seasons. So our goal towards the future is to be able to monitor this at the global scale and to be able to quantify the impact of cities across the world. And just, we've also been doing some work with United Nations Sustainable Development Goals, so there's also some implications into how do you build more sustainable cities in the future. Because if you think about it, in Las Vegas, what, if you were an urban planner, what would be some of the issues that you would have to deal with? Obviously, water use, energy use, being able to provide your citizens with shelter and whatnot. but there's also impacts on the carbon cycle. So it really cuts across all the different systems that we study, and air pollution as well. So I don't know if we have, I guess people will be asking questions, so we can stop the movie and go back to the slides, Jennifer. And I can see I'm already behind, but you tell me, Jennifer, if I'm... So that's just kind of the background of of the reasons why we did what we did. And so just let me tell you a little bit about the overall approach. And so this is based on work that Ruth DeFries and John Townsend originally did at the University of Maryland with, they were trying to create 8 kilometer and 1 kilometer AVHRR global land cover maps. And so the idea was, and let me grab the cursor here. So the idea is to start with reference data, what we call training data, at a higher resolution, and to train a regression tree or a classifier to produce data at a higher resolution, or at a coarser resolution, if you will. So our approach here is to use the NGA data. So we have 1 meter QuickBird data that we derive impervious, non-impervious at the 1 meter scale. And then we have these products located throughout the world, or these training data, if you will. And what we've done is we took the global Landsat data, so the global land survey data for 2010, and created a surface reflectance data set that is now at the Global Land Cover Facility at University of Maryland. And so we train a regression tree model to create percent impervious cover, and I'll describe the 2 data sets. So this is a percent imperviousness, or built up for every 30 meter Landsat pixel. And so in the process of doing this, Pan-Chi and the team developed something called HBASE, which is the Human Built Up and Settlement Extent Mask that we use to clean up some of our errors of commission, and also using OpenStreetMap. So just the 2 data sets that are at season currently. So the first one is the GMIS, Global Man-made Impervious Surface data set from Landsat. So it's a global 30 meter percent imperviousness estimates from GLS data. So again, the GLS data span a period between 2009 and 2011, but with the target year of 2010. So the data could vary from 09 to 11. So the values that you get in your data are range from 0 to 100%, with 100% being fully impervious, obviously. And as well, we have data clouds. And the second data set, a lot of the work that Pan-Chi did is called the HBASE, Human Built Up and Settlement Extent. And so this is a global 30 meter, I guess, binary classification, urban, non-urban as well. And it has these values, 200, 201, 202 for roads, and we have some areas with no data or clouds, and cloud shadow as well. So again, these 2 data sets are co-registered to each other, and they're really companion data sets. We also have 2 fields or associated fields of errors for each one. So just to give you an idea what this GLS 2010 looks like, so it's about 8,500 Landsat scenes acquired at the best with the least cloud. And you can see, so the top panel is true color and the bottom panel is near infrared composite. So you still see some areas of residual cloud cover. Indonesia was a particular challenge. There's also areas used a lot of data with SLC gap-filled data. So, you will see, as you zoom into the data, you will see some of those artifacts. And at the time, we didn't have any other data. Google Earth Engine was not I think it was just getting started. So was our best data set to be able to do that. And again, we were just trying to demonstrate methods that would be simple, quote unquote, and would work. So just to give you an idea of what the generation of training data looks like. So we had these subsets, and I need to re-grab my cursor. Pardon me. So we have, digital globe data, these small subsets. We use image segmentation. Our colleague James Tilton, his program called HSEG, that creates a segmented image of that. And then we had a group of analysts work through the data to generate a product that's impervious, impervious in green and non-impervious in black. And it's a lot of work, but the basic idea is you aggregate all of the pixels here to 30 meters, and then you end up with a percent impervious at the Landsat scale. And so for each one of these little squares, we have the reflectance, the NDVI, and tassel cap, and that's what goes into the regression tree. Seems simple. It was a lot of work. So anyway, so these are the training sites that we use. We had something like 2,500 high-resolution images, and we did quality assurance. We did our best, the best we could to match the data in time with the Landsat. And I think I'm going to skip a little bit here, but in total we had about 25 million or 25.5 million training pixels or reference data that we used. And this is what the data looks like for the different continents. The little red dots is the actual subsample of the Africa data. So you see a decreasing trend of greenness as you go to 100% impervious cover. And the other part that you see is you see how much of other stuff there is. And so that was one of the difficulties, is splitting out the dominant impervious from everything else. Essentially, if you see in a city, you have water, you have bare ground, you have grass, you have trees. So really, we're trying to split the impervious cover from the non, and that's a difficult problem. So I'm going to skip ahead, and I think I'm running. Jennifer, do I go until 2:35? Is that right? Would that be right?
Yes.
Okay, good.
Yes.
All right. So again, and maybe I'm getting a little too into the weeds here, but this is the way that it works. And this is a town in Hungary here, and with different a lot of agricultural fields, and the resulting product is something that might look like that. So to do that, we use a regression tree called QBIST, and one of the, we did a lot of testing and a lot of development on this, and part of the problem that we have is most of our training data was in the 0 to 25% impervious. That's just the way the real world is, actually, unless you're in the middle of a city. But so what happened is the regression tree tried to specialize or over-specialize on those areas. So we had to adapt. In our final approach, we essentially used all the samples from 40 to 100% impervious from all the continents with 0 to 40 for each continent. And we also had to do a bias correction at the end to correct under prediction at the high end and over prediction. So this is an example of the bias correction for Paris. So my green cursor, I don't know if it's very visible, but so the idea again was to push up values in the higher end to be closer to 100%. And so these results, that the bias correction accomplished this. So the big work of that Panchi developed as well is the HBASE mask, or the companion data set. And the idea Uh, so again, this is a town in Poland. So you see the outline of the town, and it's surrounded by fields, agricultural fields, and all different kinds of stages of regrowth or bare. And so what tended to happen is we had low impervious cover on some of the fields. So we had to find a way to mask those out. And so thankfully, Panchi developed this great method using the whole global archive. We actually did segmentation on the entire global archive using NASA supercomputers. And this is the methodology that Panchi developed. So the idea was to use texture features and on non-texture features as well, and to develop a feature data set that was used in random forest to create this binary urban, non-urban mask. And just to show an example of why we had to do this, so this is the GLS data that we were using, and you can see the difference in seasons and the impacts that it might have. So our baseline method would have looked maybe something like that, and then after Panchi's work, we constrained the urban footprints, so which was solved a lot of issues. So just to show you a couple of the results, so on these upcoming panels, we have what Google Earth looks like, the VIIRS day-night band, 750 meters. This is a land cover. On the lower left is a land cover map from the Chinese Academy of Sciences called Global Land Cover, or Global Land 30. So it is based on Landsat, and this is our GMIS data set. So I'm just going to cycle through. So this is now Paris. And the point that we were trying to make is again, this is 30-meter data, so a lot more spatial detail. And with the percent impervious, it also gives much more detail in areas of urban sprawl, for example, or lower density urban areas or regions. So this is Washington, D.C., and I have a little zoom in just to show you what I'm talking about. So this is actually the window, what it would look like, and Sri is going to talk about this, what it would look like using the tool to download the data. So this is Washington, D.C. If you're not familiar with it, this is the National Mall. Here is the U.S. Capitol. And you can actually see that little dot there is the Washington Monument. So we're capturing details. And what you can see, again, in this area, we have very good contrast between forest and non-forest, but you see the amount of detail that's available in this data set. You can see street patterns. And so again, you know, we hope that users will find this useful. It's probably not you know, the same in terms of error quality as a national land cover data set, which is tuned regionally. But you know, it's quite good, and it's useful for a lot of. It should be useful for a lot of different purposes. And this is where I'm talking to you from Goddard Space Flight Center. And so just to give you a couple of ideas on the accuracy. So we didn't do a full validation with independent data, but we used what's called cross-validation performed by continent. So you're doing subsets of the training data using, you know, one block to run the regression tree and another block to assess your results. And so these are the results. So the RMSE after the bias correction and the mask, the HBASE mask, range from about 11% to 18% for Europe. And ironically enough, Europe was our first data set, so I think it may be something that we need to revisit to see if we can improve those results. But globally, we have a root mean square error of about 14%, and so if you consider the national land cover data set for the USGS is about 7 to 10% error, I think we're doing really good, considering we have a global tune data set and global run data set again. So just to finish up with a couple of things, so our next steps and things that we're working on, we're try to keep on improving the data sets and finish publications. And so I'd like to encourage you, if you're here, you're interested in the data, and please feel free to send us feedback. And again, you know, we realize the data set is not perfect. We're missing some data in Indonesia, and there's places with cloud cover, but we want to keep improving it. And we're continuing comparisons with other data sets. And the next kind of step is to try to see, you know, could we use something like Google Earth Engine or some other, you know, consistent surface reflectance data set to do a time series of the same data set. Again, I think this kind of, it really challenges a lot of the machine learning methods, again, because of the distribution of the data and obviously applying things globally. If you think it's 8,500 scenes and each scene has, you know, 150 million pixels each, you can understand the difficulties. So some of the other work is also exploring the other dimensions of the urban footprint, the vertical domain, the different spectral signatures. So there's a lot of opportunities to keep studying urban areas from space and with new technologies and new sensors. Who knows what you guys will find. And finally, I've done a lot of education and outreach in the past, and I think I just want to put in a plug that obviously, and you know, I don't know how many of you currently joining in are living in cities, but I suspect a lot are. But so there's a lot of opportunities for stories and public outreach. After all, we all live in cities, and so it's a personal experience that I think we can connect to much more directly than other issues, and it's things that impacts our own communities, our schools, the places we live, the places we work, so on and so forth. So I think there's a lot of opportunities to do that, and so I just put a plug for Citizen Science, this Global Observer. And I have my last slide, and I know, you know, the September 22nd to the October 1st is already passed, but I just wanted to highlight this phone app that we've developed with the GLOBE program, where you can actually do land cover observations on your smartphone and help NASA better understand the, you know, the accuracy of their products and verify the accuracy of our data. And so I think with that, I will leave it. And you know, thanks again for listening. And Cheng and Panchi and myself look forward to hearing from you. And if you have any issues with the data, and so I will pass it on to Sri. And thank you very much.
And thanks, Jennifer and Eric again. Let me share the screen. Can you see the web browser on my screen, Jennifer?
Yes, I can. Thank you.
Thank you. So thanks, Eric, as well. So greetings, everyone, and thanks for listening. And so as Eric mentioned, the team at the SEDAC, one of the NASA data centers, SEDAC, and Eric and his colleagues worked together to distribute and make these data sets available through the SEDAC website. So I'm going to talk today about how to find more information about the GMIS and HBASE data sets, how to explore the data set and visualize them and around the study areas of your interest, and then how to download those data sets. So those are the three main components I'm going to cover today. So how do you find more information about these two data sets? If you go to the SEDAC website, you can Google search, but the address is sedac.columbia.edu. So go to the SEDAC website and do a search for GMIS in the search box right here on top right. Make a search, and it will come up with two results, the GMIS dataset and the companion HBASE dataset. So go ahead and click on one of these datasets. Let me click on the GMIS dataset. And so this overview page gives you a little bit description about what the dataset is, a short abstract, and a recommended citation over down here. If you download this data and use it in your work, we request you to use this citation here. I keep highlighting the wrong thing. Okay, let me scroll up. So you have a brief description here. Let's see how can you find more detailed information and the methodologies that Eric was describing in his presentation. Go to this documentation tab here, and there's a link to, there's a link to detailed documentation here. It's in PDF format. So let's click on that. Let me zoom in here a little bit. So more details about, here is the table of content about the dataset, and the methodology is listed here in this paper. And you can read it at your convenience. Let me go back to the other tab. Let me close this tab for now. Okay. And we also provide some static PDF maps illustrating the data sets. So if you click on the Maps tab here, let me cancel this, and click on one of these PDF maps, you can see some comparisons to give you a taste of how these maps look like. Let me close this. Let's get back to the dataset page. Okay, so you read a little bit about the dataset, read the documentation. You can explore the metadata in more details by going to the metadata tab here. This is kind of formal standard metadata. But now that you're really interested in the data set and you want to really explore more the actual data and download it maybe to consider for your work. So to visualize and download the data, go to this data download tab, just click on it. And to download the data, you're going to have to log in using your NASA Earthdata account. Many of you may have an account with NASA Earthdata. If not, it's very easy to register for one. You just have to provide some very basic information like name and email address, and you can get an account. Once you have an account, you can log in through this link here. Let me log in with my own account. And it puts me back into the web page where I started the login process. So here there are links provided for exploring and downloading the two data sets. Let me do some exploration using one of these mapping tools that we developed at SEDAC. So let me click on the Explore link here, open it up in a different tab. So this mapping tool provides you a 4-panel view where you can compare different data layers from these two data sets and visually analyze them a little bit. So on the top left here is the GMIS, the impervious percentage data layer. On the top right is the error estimation related to this percentage. In other words, what is the possible expected error in this estimation. And on the bottom left here is the HBASE, human built-up and settlement extent data layer. It's like Eric said, it's a binary mask saying a pixel is in a built-up area or not. And on the bottom right here is the probability of pixel being in a built-up area. In other words, it's a measure of accuracy as well. So the left layers are the main data layers here, and the one on the right are the errors or probability associated with those estimates. So I really want to, let's say as a user, I really want to explore into an area of interest and really see how this data set looks like. So let's say I live in New York, so let's say I want to see how my neighborhood looks like in terms of urbanization. So I'm interested in, let's say, Central Park in New York area. So let's search for Central Park. And the map zooms you into the Central Park area. But I want to explore even more in depth. I want to zoom in even more. So what I can do is click on this single map or full screen view here. Click on this icon, and it puts the map, enlarge it to the full screen, and I can zoom in all the way down to the native 30-meter resolution. As I zoom in here, the Central Park area is going to come into view. Let me zoom in one more time. So as you can see, Central Park is a really grassy area in the middle of a very highly urbanized city, that is New York City in Manhattan. So you can see, zoom back. You can see how the data set actually delineates the impervious surface areas against the non-impervious surface areas here. It's pretty clear here, this rectangle Central Park is clearly identified. There you go, much better view. The image just took some time to load. So it really nicely delineates the Central Park area from the surrounding highly urbanized New York City area. I can further zoom in. That's the highest zoom level. So at this highest zoom level, what you are seeing is 30-meter resolution pixels. Give it a second to fully load. One more time. Okay, so what you can see here is there is a tennis center at the middle of the Central Park, and it's surrounded by grassy areas and a reservoir here down below. So the algorithm is pretty nice, pretty good actually in delineating these pixels and classifying them correctly. So let me go back to the 4-panel view by clicking there and explore some pixel values and see what they say. Let me click on this, one of these pixels in the tennis center here. Looks like I am stuck here. Okay, let me see. I'm supposed to get pixel values here. Okay, let me reload this map. Good. Let's do the search again. Central Park. Excuse me for a second, screen got stuck here. Okay, there we go. So let me zoom in a little bit more. Further down, zoom in, zoom in, zoom in. Give it a second to load the high resolution image. Pardon me for the delay here. It always happens. I have tried this demo a few times, but when it's time for the prime time, something goes wrong. Okay, never mind. Here we go. So I can click on a pixel here. That was that tennis center I was talking about. And there you go. So it says 96% imperviousness. That pixel I clicked on has a 96% imperviousness, meaning it's completely built up. And the error percentage associated with that pixel was 27%. So you can look at the legends here. So this shows the error percentage. This legend here, it shows the imperviousness percentage. And you can look at the other values as well. So let me close this. So now that we have explored a particular area in depth, let me show you how you can compare different cities actually to see how the urbanization pattern compare between different cities. So I'm going to put the impervious map on all 4 map panels here by unsyncing the panels first and repeat the map. Say OK. So now you're seeing the impervious surface map on all 4 panels here. So let me zoom in into Washington, D.C. here. So let's search for Washington, D.C. Zoom out a little bit so I can see a larger area. On this panel here, let's go to Paris. Zoom out a little bit to see more details. On this one, let's go to Beijing in China. Zoom out a little bit. And on the 4th one, let's go to New Delhi in India. Let me zoom out a little bit. Okay, it will take a moment to load. Okay, there you go. So right now I'm focused into 4 different cities around the world. So you can see Paris is fairly densely urbanized because the higher impervious surface percentage illustrated in dark blue. Whereas Washington may be a little bit less densely urbanized, but is spread out a bit more. It extends to a larger area. Similarly, Beijing and New Delhi are densely urbanized, as well as sprawling out to extending out to larger area around them. So you can do these comparisons, visual comparisons and exploration of the data values a little bit, and let's see how we can download this data set. So click on this download button on the top right, and it brings this single map view where you can choose to download using different criteria, by a country, by a UTM tile, or by uploading a shapefile, or by drawing a rectangle or polygon. Let me turn on the impervious surface layer. So let's say I am interested in studying Mexico country as a whole. So I want to download the data set for Mexico. So let's select country as the download mechanism. And click on the download button. Let's get rid of these instructions here. What happens is a country mask is overlaid on this map so that you can choose the country of your interest. So let's say I want to download France, data for France. Click on France, and a dialog pops up asking you to make further selections. So we provide this data set in 3 resolutions, the native 30 meter, a coarser 250 meter resolution, and even coarser 1 kilometer resolution. Let me stick with the native 30-meter resolution here. And we also provide two projections, the UTM zones, as well as a geographic let-alone projection. Let me choose geographic here. And let's say I want to download the two main data sets as well as the error or accuracy layers. So I select all four and then just click on the Save button. And here, 4 links are provided for downloading the 4 data layers I selected, as well as a link to documentation and links to overview of the dataset overview pages are provided as well. We get back to the downloads. Let me show you, just click on this, and what happens is a zip file containing the data for France is downloads to your desktop. And it just finished downloading here. Let me click on that. And the zip file contains a GeoTIFF format dataset for France, as well as some brief documentation about the dataset here. So you can extract it to your desktop and use it in your analysis, use it in your work. Let me close this. Close this. Let me exit out of the country download mode. Let's say I'm not really interested in a whole country, but I'm doing a study in a city or a city and the surrounding area. So click on the tile, click on the download button. And here you go. The tile mask is displayed on the map. Let's say I'm doing a study of Dar es Salaam in Tanzania. So click on this tile here. Let me zoom in a little bit. Click on this tile here. And I'll stay with 30-meter resolution, keep the projection as UTM, select my data layer, and click Save. And I get the link to download the data. Let's exit out of this tile mask. And the two other interesting ways of downloading the data set is by drawing your own rectangle on the map. So let me turn that on. Let's say I want to download the data set around Nairobi. I can draw a polygon by clicking here, define the area of interest here, close these instructions, click on the download button, close the instructions, and click the polygon I just drew to select it. And I'm going to get a coarser resolution, 1 kilometer data, let's say, in geographic projection. Click on the data layer and click Save. Since this is a custom subsetting, because the area is actually defined on the fly, the subsetting will take few seconds before it gives you back the data. There you go, not too much time. And so you can download the data this way as well. We exit out here. The final method of downloading is by uploading your own shapefile. So select the shapefile mechanism. Choose a zip file that contains all these components of a shapefile in a zip file. So I'm going to choose Texas with its counties. Let me open that and let me submit it. It says the shapefile has many polygons. Do you want to combine all of them into one? I am going to say no. So let's say okay. What happens is the Texas shapefile is overlaid on the map. And now I can click on any of these county polygons in the Texas shapefile and download data for that area. So let's click on download, close these instructions, zoom in a little bit. And let's say I'm interested in the Houston area. So let's click on that polygon. Same dialog pop-up comes up. I'm going to pick coarser resolution, geographic projection, and say save. So again, this is a custom download, custom subsetting, so it might take a few seconds to complete. While it's doing its work, there you go, it's done. So you can download the data that way as well. So that completes the 4 methods of downloading this data set. And as a concluding note, I would like to say if you define a very large area by drawing a polygon or a rectangle or uploading a shapefile, which is larger than 300,000 square kilometers, then we cannot fill the request on the fly. What we will do is queue up your request, and we will send you an email with the links to download the data after a few hours or whenever that processing is done. So
Okay,
at this
Sheree,
point, I would like to finish. Thank you so much. Thanks, Jennifer.
Okay, thank you, Sheree. Thanks, everybody. We are running a little bit long today. At this point, what we will do is we'll move to the Q&A. We'll move to the final set of polling questions. We'll give these just a couple of minutes or so, and then we'll move directly to the question and answer period. And then I just wanted to say a couple words about that. If we do not, there's quite a few questions that need to be addressed, and if we run out of time in addressing those questions live during today's webinar, what we'll do is we will provide those questions to our speakers as well as the principal investigators who are also on the line, and we will have them follow up with you offline. So hopefully we'll be able to get to a good chunk of the questions today, but if not, no worries. We will have our speakers address those separately offline with you. All right. Well, thanks, everybody. Let's give this just another minute or so and then move to the Q&A. All right, everybody, we're going to give these just a few more seconds here and then move directly to the Q&A. But I will leave the virtual meeting space open until 3:30 p.m. after the Q&A is complete. If you think of something, feel free to, notate that within the Q&A pod. All right. At this point, we are going to transition to the Q&A period. As I said, we have quite a few questions, so if you would bear with me for a moment that I can kind of get back to the start, where we've got our first question, which was rather early on. So, okay, let's see here. I am trying to... Okay, one of our first comments was whether or not the slides are downloadable. And again, if you're interested in receiving a copy of the slides, you would need to email our speaker directly. Our first question, I'm going to pull that up now, and I leave it to all of our panelists to determine who answers the question. My question or concern will be concerning the rapid loss of vegetation due to an increase of urban development. This would surely increase the overland surface runoff from precipitation within highly urbanized watershed. So could floods be worsened in the near future?
This is Eric here. I mean, that is kind of exactly what happened in Houston with Harvey. there's a lot of development over the last 20-some years. So it's not only loss of vegetation, but it's the building up of these surfaces that don't allow water to penetrate. So essentially what happens is rain falls and it just runs off directly into the streams. And so one of the slides that I had, what happens is not only does the water run all off into the streams, but there's a lot shorter time period between the rain event and when it gets to so it tends to exacerbate issues with flooding, to create more flooding, but also to shorten the time that people have to react. So yes. And that is one of the main applications of these data sets, is for watershed modeling as well.
Okay, thank you, Eric. And we have a follow-up to that. Urbanization in tropics is escalating. I'm doing research for flood forecasting in that region. Is there data for impervious area for Panama?
Yes, there is. I think there was, I did answer a question on Panama. One of the issues in Panama, and sort of the same thing in Indonesia, is for this particular data set, there's a lot of cloudiness. And so I don't, I know we have data for the entire globe, except for one area in Indonesia, but we would probably be limited to the cloud cover. So one of the questions, one of the ways, or one of the things that we're doing is this idea of using time series. So we're using, instead of one shot in time, we can use the seasonal change, so that we try to avoid cloud cover. And I think Google Earth Engine has ways of also processing data where you can sort of composite the clouds out. But we do have data. The data sets are global, so there should be data for the entire globe, except, again, one smaller in Indonesia and Antarctica. Okay. Sorry.
Yes. Well, thank you so much, Eric. I appreciate that. Our next question is, I looked into a few of the impervious raster data sets. They still are not as accurate as doing your own supervised classification with a Landsat image, albeit it is time consuming and does require a priori knowledge of the area of interest to be accurate.
Okay. Well, I mean, I'd be interested. The results that we've looked at look actually quite comparable to the National Uncovered data set. So we'd be interested if you have any issues in a particular region. The point I did make about the National Uncovered data set, and the same thing that the question asks, is obviously if you're looking at a small area and you know the area very well, you can probably do a better job. And our goal was to create a global data set with methods that were repeatable and semi-autonomous, or automated. So
okay, wonderful.
Different goals.
Thank you,
But
Eric.
Thanks for the feedback, though.
Yes, that's very useful. So our next question is, I'm a graduate student at American University studying international relations. I'm curious if impervious cover means specifically to rainfall, or does it constitute other factors? Not sure if I...
I mean, obviously we think of it's impervious to water, but obviously it would have other impacts. I mean, nothing else. There wouldn't be any root growth, soil moisture, vegetation growth, although you do see some roads where, or some areas where you have vegetation growth. So it is impervious to a lot of things. I hadn't really thought about that, but that's a good point.
Okay, thank you, Eric. And our next question is, are you only obtaining the training data and validation from the segmented VHR, or are there other sources of training and validation data?
No, for this project, that's entirely what we used. For the HBASE mask that Panchi Wang developed, he developed some training data directly from the Landsat data, but that was a different product. For the regression tree and the GMIS, it was all. Actually, I take that back. We did add some training data for snow in the European data set. So, but it was a majority was the high resolution data set, or very high resolution. Hopefully that made sense.
Yes, thank you so much, Eric. We're working our way down the order of the questions as they were first received, so I definitely am not trying to lose sight of any of the questions. There are a couple that are more off topic and should be, we can certainly address those offline, but I am working my way down. So
yeah, and I mean, while you're doing that, it was really gratifying to see everybody joining from, I mean, all kinds of places all over the world. So it's great to reach across the globe, and yeah, it's really awesome. So thanks.
Okay.
Thanks for everybody, even at 4 a.m. in Tokyo.
Okay, so the next question is there any reason for using QBIST over other ensemble tree methods?
No, that's a good point. It is something that we've used in the past. So Cheng Huan worked on the National Land Cover Dataset, which was using QBIST as well. And so we had experience. It was easily available, and that's what and again, at the time, I don't think random forests and things like that were necessarily available. So I've done a lot of work as well with C5.0 and QBIST, and it's not an endorsement, but it's work that we've done in the past with tree cover and impervious cover, and good results.
Okay, excellent. Our next question, are the data produced by airborne tools? This particular user needs oblique images, not vertical, developed by satellites.
No, I mean, it's you could use that in the future, obviously, and there could be certain applications, obviously, for those kinds of data. But for here, I mean, there's no. Again, we're trying to create a global data set, a continental scale models, and so we had to use what was available. And luckily, we had the very high resolution data set available through NASA. And then obviously the free Landsat archive really made this possible. But yeah, in the future, there's no reason why you couldn't integrate not only data from airborne, but also potentially different sensors to get different kinds of information into the classification.
Okay, thank you, Eric. Our next question, I see that our speaker had answered several questions, which I'm very thankful for because we have a tremendous amount of questions here via the Q&A pod. So our next question is, from an emergency management perspective, specifically related to raising alerts. Oh, excuse me, there's no question there. It's more of a comment that it would be, this data will be useful for...
Yes, I saw that. Thank you.
Okay. Pardon me. My question, okay, Eric, you're answering that one.
Yeah, and, just to tag on to that comment, obviously, with the fires that we're having in California, it's very important to have these kinds of tools. Obviously, the U.S. government has data from the USGS for built-up area, but again, for parts of the world where this is not available,
Right.
it could be very important.
Okay, thank you. So one of the comments that was made is, having a brief discussion on urban indices for estimating urban impervious surface, along with a comparison in present work. I'm not sure if there's a sufficient detail.
Yeah, I don't see that. I don't see the comments where you have. But can you repeat that again?
Sure. So it says, I would like a brief discussion on urban indices for estimating urban impervious surface along with a comparison in present work.
Wow, this sounds like my dissertation professor here asking me questions. um, yeah, I mean it's kind of a long it's a long question. I don't think there's no comparable data sets globally. I think the Europeans have created an urban data set over time, but it's not the same time period as ours. And the comparison that we're looking to run is something that compares with the National Uncovered Data Set over the U.S., although different parts of the U.S. Our results are quite comparable, just at least spatially. And I'm trying to think. So in terms of this comparison, the other one available at the 30-meter scale would be this Chinese Academy of Sciences data set. So that's a possibility. And again, so we're talking about global 30-meter data sets. So the work of intercomparison is a difficult one, even picking random samples.
And
I think that
go
there
ahead.
was another element to the question as well. Jennifer?
Okay.
Oh, wasn't there like the last part, a discussion of?
It said a brief discussion on urban indices for estimating urban impervious surface along with a comparison in present work if possible. But
Right.
Yeah, it might be something we can address further offline because.
So maybe they were talking about indices, there's any number of spectral indices, and we did not use any of those, but in current work we're looking at doing that, and also trying to figure out if we can do something that takes into account the whole seasonal evolution of these indices.
Okay.
But we haven't done anything like that.
Okay, well, thank you, Eric. And our next question, there's a question regarding, does anyone know if this data can be used to measure damage and or recovery efforts, or recovery from natural disasters?
Well, I mean, it is a one shot in time. So it's a 2010. So if there's changes related to that, then those kind. I mean, originally we had an idea of doing a 2000 to 2010 change. We were not able to do that, but so yeah, you would be able to, but I don't know that this data set would be the best way to do it. You could use a Landsat before and after image. I mean, at least you could determine the areas that were built up and impervious in 2010 and see if those have changed. But that would have to be done using the Landsat data or Sentinel data if that's a possibility as well. But yeah, the data are used quite a bit. The Landsat data are used quite a bit for fire recovery. So, those kinds of studies can be done.
Okay, thank you. We only have, really time for basically one more question here, and then we'll have to, send the Q&A log to our speakers as well as the principal investigators who are also online and have them follow up separately with you. So our last question for today is, how does the presence of green roofs in urban areas affect your estimates of imperviousness?
Well, I mean, it is, that's a very good point. From essentially the perspective of space or from Landsat, what you see is what you see. And so if the roof is green, we would probably mask it out as green. So that is one of the limitations, certainly. And that's also another kind of segues into areas of research is well, so if we had ways of seeing that it's a green roof, but it's in an elevated, so if we had that third dimension from LiDAR data sets, for example, we might be able to say that, there's a big building underneath. And similarly, so if you have, have a road that runs under a forest, you'll still just see the treetops and won't see the road. So that's also an area where we're missing. And so if you had that third dimension, you might be able to do better. But certainly there's room for improvement, and we're working on that. Obviously, having the time series of data, so having a whole year of data so that you can interrogate whether that green roof may have gone. It still would cause confusion, but so that's work that's continuing.
Below in the file sharing pod that we do have the Landsat Las Vegas animation as well as the final agenda. But again, if you're interested in receiving a copy of the PowerPoint slides, please do email our speaker. So at this point, what we'll do is we will log off from the audio component of the webinar, and we will leave the virtual meeting space open for those of you who may have additional questions or you think of something. Please jot it there into the Q&A. Thank our panelists who also logged on from the science team. I'd like to thank Sri, Eric, and all of you for spending time with us today. I should have the direct link to the recording as well as a YouTube link for today's webinar posted by Friday. And I will email not only those of you who were able to participate, but those who registered and were unable to attend today. So with that, thank you, everybody. We'll log off from the audio component, and I hope to see you at an upcoming webinar. And again, Eric and Sri, if you don't mind staying in the virtual meeting space for another 10 minutes, that would be very useful.
Yeah, and thank you very much, Jennifer, and thanks to everybody online, and Cheng and Penchi as well, my co-Is who joined online, and thanks for all the good questions.
Yep, thank you, everyone. Yep.
Yes, excellent, everybody. We'll log off now, and I hope to see you online soon.
Thank you.
Thank you. Bye-bye now.
Bye-bye.